What if reality is far stranger than anyone ever imagined? Deep inside some of the world's most powerful quantum computers, scientists are witnessing behavior that seems to challenge our most basic understanding of the universe. These machines aren't just solving complex problems. They may be exposing something unsettling about the nature of reality itself. Some researchers believe quantum experiments are revealing patterns that shouldn't exist. Others admit they have no explanation at all. Tonight journey into the strange world of quantum mechanics, where particles appear to ignore common sense, and where every new discovery raises even deeper mysteries about the universe we live in. If you enjoy relaxing science documentaries that explore the biggest questions in existence, be sure to like this video, subscribe to Cosmic Bedtime Stories, and join us for tonight's journey into one of the most baffling mysteries ever uncovered. Classical computing systems emerge from the gradual development of electrical engineering, mathematics, and materials science, forming a structured environment in which information is represented through stable physical states inside machines built for predictable control. At the macroscopic scale, these systems appear as organized assemblies of circuits, wiring, and silicon-based components that guide electric charge along carefully designed paths. The behavior of such systems relies on classical physics, where outcomes are determined by measurable initial conditions and well-established rules of current voltage and resistance. In this framework, information is not abstract, but physically encoded in the presence or absence of electrical signals, forming patterns that can be reliably stored and manipulated over time. Inside these systems, binary representation becomes the fundamental language of computation. Electrical states are interpreted as two distinct conditions often associated with high and low voltage levels. These states are stabilized through circuit design that resists small fluctuations caused by thermal motion or environmental noise. The stability of binary systems depends on materials that can maintain clear thresholds between conductive and non-conductive behavior, allowing signals to be interpreted without ambiguity. This macroscopic clarity forms the basis for all higher levels of computation, from simple arithmetic operations to complex data processing tasks. The physical architecture of classical computers is built upon layered organization. At the largest scale, there are complete machines that integrate power supplies, cooling systems, and communication interfaces. Within these machines, circuit boards distribute electrical pathways across structured grids. Beneath this level, individual integrated circuits contain millions or billions of microscopic switching elements. These elements operate in synchronized patterns governed by clock signals which regulate the timing of state changes across the system. The coordinated rhythm of these signals ensures that computations proceed in ordered steps rather than chaotic transitions. Electrical conduction in these systems is governed by the movement of electrons through conductive materials such as copper and doped silicon. The flow of charge is influenced by electric fields established across components, guiding electrons through predefined routes. Resistance within materials converts some electrical energy into heat, which must be managed to maintain system stability. Cooling mechanisms, often involving air or liquid circulation, maintain operational temperatures within safe ranges, preventing structural degradation of components. This thermal management becomes a constant background condition for reliable computation. The design of classical computing systems also depends on the predictable behavior of semiconductor junctions. These junctions form the basis of switching devices that can rapidly alternate between conductive and insulating states. The ability to control these transitions allows for the construction of logic gates which perform fundamental operations such as combination selection and inversion of binary signals. By arranging these gates into larger networks, engineers create functional modules capable of performing arithmetic memory storage and data routing. Each layer of complexity builds upon the stability of the layers beneath it. Memory systems within classical computers store information through stable electrical or magnetic configurations. These configurations persist even when active computation is paused, allowing systems to retain data for extended periods. The physical encoding of memory depends on carefully maintained structures that resist unintended changes caused by external interference. Over time, these structures form large-scale repositories of information, enabling software systems to operate on persistent datasets rather than transient signals alone. As computational systems scale upward in complexity, synchronization becomes increasingly important. Clock cycles act as a unifying rhythm, ensuring that different parts of a processor update their states and coordination. This synchronization prevents inconsistencies that would arise if components operated independently without shared timing. The precision of these timing signals is maintained through oscillating circuits that produce stable frequency references. Even small deviations in timing can influence the reliability of computation, requiring careful engineering control. At the level of software execution, classical computation translates symbolic instructions into sequences of physical operations. High-level programming languages are compiled into machine instructions that correspond to specific patterns of electrical activity. These patterns move through processing units, triggering logical transformations that manipulate data stored in memory. The entire process remains grounded in physical reality, where each abstract operation corresponds to measurable changes in voltage and charge distribution. The reliability of classical computing systems depends on redundancy and error management. Noise from electromagnetic interference, material imperfections, and thermal fluctuations introduces small uncertainties into signal transmission. Engineering solutions compensate for these effects through error detection and correction mechanisms, ensuring that information integrity is preserved across long sequences of computation. These safeguards allow large-scale systems to function consistently even in imperfect physical environments. In advanced systems, integration density increases as more components are placed within smaller physical regions. This densification enhances performance, but also increases sensitivity to heat and electrical coupling effects between nearby elements. Careful material selection and architectural design mitigate these challenges, balancing performance with stability. The resulting systems represent a refined equilibrium between physical constraints and functional capability. Across all scales, from large machines to microscopic switching elements, classical computing remains grounded in deterministic physical behavior. Each computational step reflects a direct transformation of electrical states governed by classical laws. The predictability of these transformations allows engineers to design systems with high reliability, forming the technological foundation upon which modern information processing is built. This macroscopic framework provides the stable environment from which more sensitive regimes of physical computation begin to emerge in deeper layers of scale. Semiconductor materials form the core physical medium through which modern computational systems operate, and their behavior emerges from the structured arrangement of atoms within crystalline lattices. In these solids, electrons occupy energy bands that define whether charge can move freely or remain restricted. The distinction between conductive and insulating behavior arises from the spacing between these energy levels, which is shaped by the type of atoms involved and the regularity of their arrangement. Silicon, one of the most widely used semiconductor materials, provides a stable lattice structure that can be precisely modified to control electrical properties. The process of doping introduces small amounts of impurity atoms into a pure semiconductor lattice, altering its electrical behavior in controlled ways. When atoms with extra valence electrons are introduced, the material gains additional free charge carriers, forming what is known as N-type material. When atoms with fewer valence electrons are introduced, the material develops a tendency to accept electrons, forming P-type material. These two modified regions create conditions in which electrical flow can be carefully regulated, forming the basis of controlled switching behavior. At the junction between P-type and N-type regions, a boundary forms that exhibits directional electrical properties. This region, known as a PN junction, allows current to flow preferentially in one direction, while resisting flow in the opposite direction. The behavior of this junction depends on the formation of a depletion region, where mobile charge carriers are temporarily reduced due to recombination effects. Within this region, an internal electric field develops that influences the movement of electrons and holes, shaping the overall response of the material to external voltage. The ability to control charge flow at these junctions enables the construction of semiconductor devices that act as switches. When external voltage is applied in one direction, the barrier at the junction is reduced, allowing current to pass. When voltage is applied in the opposite direction, the barrier is strengthened, preventing current flow. This directional control forms the basis of rectification, amplification, and digital switching, which are essential functions in computational hardware. Transistors, the fundamental switching elements in modern electronics, are built using combinations of semiconductor junctions. These devices operate by controlling a larger current flow through a channel using a smaller input signal. The structure of a transistor allows it to function as an electrically controlled gate, capable of switching between conductive and non-conductive states at extremely high speeds. The reliability of this switching behavior depends on precise control of material composition and geometric structure at microscopic scales. Within integrated circuits, millions or even billions of transistors are arranged into complex networks that perform logical operations. The arrangement of these components is determined through photolithographic processes that etch patterns onto semiconductor wafers with extreme precision. Light-based fabrication techniques allow structures to be defined at scales approaching individual nanometers, enabling the continued miniaturization of computational devices. As these structures shrink, quantum effects begin to appear, although classical behavior remains dominant in most operational regimes. Electron motion within semiconductor devices is influenced not only by applied electric fields, but also by interactions with the atomic lattice. As electrons move through the material, they scatter off vibrating atoms, which introduces resistance and contributes to heat generation. This thermal energy must be dissipated to prevent damage and maintain stable operation. The relationship between electrical performance and heat production becomes increasingly important as device density increases, requiring careful thermal engineering at both chip and system levels. The switching speed of semiconductor devices depends on how quickly charge carriers can respond to changes in applied voltage. Faster switching enables higher computational performance, but also increases energy consumption and heat output. This creates a balance between speed efficiency and stability that governs the design of modern processors. Engineers optimize this balance by adjusting material properties, device geometry, and circuit architecture. At larger scales, semiconductor devices are integrated into layered systems that distribute computational tasks across specialized units. Some regions handle arithmetic operations, while others manage memory access or signal routing. This division of labor allows complex computations to be performed efficiently, with each subsystem optimized for a specific function. The coordination between these regions depends on precise timing signals that synchronize state changes across the entire chip. Noise in semiconductor systems arises from multiple sources including thermal fluctuations, material imperfections, and electromagnetic interference. These small disturbances can introduce errors into electrical signals, but modern design techniques incorporate shielding, filtering, and redundancy to mitigate their effects. The resilience of semiconductor-based computation depends on the ability of these systems to maintain clear signal distinctions despite the presence of physical variability. As integration continues to increase, quantum-scale effects begin to influence the behavior of electrons within semiconductor structures. Tunneling, a process in which particles pass through energy barriers that would be insurmountable in classical physics, becomes more significant at very small scales. Although these effects are usually controlled or minimized in classical computing systems, they represent the beginning of a transition toward regimes where quantum behavior cannot be ignored. Despite these emerging quantum influences, semiconductor systems remain largely governed by classical electrical principles at operational scales. The predictable behavior of doped materials, junctions, and transistors allows engineers to construct reliable computational architectures. These architectures form the bridge between macroscopic electrical systems and the microscopic quantum phenomena that will become more central in deeper layers of physical exploration. Cryogenic control systems define the operational environment in which advanced quantum devices are stabilized, and they rely on extreme reduction of thermal energy to bring matter close to the lowest achievable temperatures in the universe. In this macroscopic setting, temperature is understood as the average motion of particles within a material, and lowering it reduces the random vibrations that normally dominate atomic scale behavior. As these vibrations weaken, physical systems begin to reveal delicate properties that are normally masked by thermal noise, allowing quantum effects to become observable and usable in engineered devices. The cryogenic environment is typically achieved through layered cooling stages that gradually remove heat from a system. Each stage operates at a lower temperature than the one before it, forming a cascade that carries energy away from the central experimental region. At the deepest levels of cooling, temperatures approach fractions of a degree above absolute zero, where atomic motion becomes extremely limited. In this regime, even minor external disturbances can influence system behavior, requiring careful isolation from vibration, electromagnetic interference, and residual heat sources. Materials behave differently under these conditions compared to room temperature environments. Electrical resistance in certain conductors decreases significantly, and in some cases materials enter a superconducting state where electrical current flows without measurable resistance. This phenomenon arises from the formation of paired electron states that move coherently through the lattice without scattering. The absence of resistance eliminates energy loss through heat in these specific conditions, allowing highly stable electrical circuits to be constructed for sensitive experiments. The stability of quantum devices depends on maintaining this low-energy environment consistently over time. Even small temperature fluctuations can disrupt fragile quantum states, causing them to lose coherence and revert to classical behavior. Cryogenic systems therefore include extensive shielding and feedback control mechanisms that continuously monitor temperature and adjust cooling power to maintain equilibrium. The precision of these systems is essential for sustaining conditions under which quantum information can be reliably stored and manipulated. Within this cold environment, atomic and subatomic particles exhibit reduced thermal agitation, allowing quantum mechanical effects to dominate their behavior. Particles such as electrons and superconducting current carriers can occupy collective states that extend across macroscopic distances. These states are highly sensitive to external influence, meaning that even minimal environmental interaction can alter their configuration. This sensitivity is both a challenge and an opportunity, as it enables precise control of quantum systems while also requiring extreme isolation. The engineering of cryogenic chambers involves multiple layers of insulation that prevent heat exchange with the surrounding environment. Vacuum spaces are often used to eliminate conductive and convective heat transfer, leaving only radiative processes as a source of energy exchange. Reflective shielding materials reduce radiative heat flow further by reflecting infrared energy away from the cold interior. These combined strategies create a highly controlled thermal environment that supports quantum experimentation. Mechanical stability is equally important in cryogenic systems, as vibrations can transfer energy into the system and disturb delicate quantum states. Specialized mounting structures isolate experimental components from external motion, while damping systems reduce internal mechanical resonance. Even microscopic shifts in position can influence quantum coherence, making structural stability a fundamental requirement of system design. At these temperatures, electronic components behave differently than they do under normal conditions. Semiconductor properties can change, and superconducting circuits become viable alternatives for traditional electronic systems. These circuits are capable of operating with extremely low energy dissipation, which is crucial for maintaining quantum coherence over time. The integration of superconducting elements allows researchers to construct controlled environments in which quantum behavior can be studied with high precision. Thermal radiation within cryogenic systems becomes significantly reduced but not entirely absent. Residual photons can still interact with quantum devices, introducing small disturbances that must be accounted for in system design. Shielding and filtering techniques are used to minimize these interactions, creating an environment in which quantum states are influenced primarily by intentional control signals rather than random environmental noise. The transition from classical thermal environments to cryogenic conditions represents a shift in the dominant physical processes governing system behavior. Instead of being driven by chaotic thermal motion, matter begins to exhibit structured quantum properties that depend on wave-like behavior at microscopic scales. This transition is gradual and depends on both temperature and material properties, with different systems requiring different thresholds to enter quantum-dominant regimes. As cryogenic control systems become more refined, they enable increasingly complex quantum devices to operate reliably. These systems form the foundation upon which controlled quantum computation can be built, providing the stable environment necessary for manipulating fragile quantum states. The reduction of thermal noise at this scale reveals a deeper layer of physical behavior, where classical intuition begins to lose predictive power and quantum dynamics become the primary governing framework of the system. Physical qubit realization emerges within cryogenic environments, where carefully engineered systems are designed to isolate and control individual quantum degrees of freedom. In this setting, a qubit is not an abstract object, but a measurable physical configuration of matter that can exist in two distinguishable quantum states. These states are typically represented through properties such as energy levels, magnetic orientation, or charge distribution, depending on the chosen physical platform. The stability of these states depends on maintaining conditions in which external disturbances are minimized, and quantum coherence can persist long enough for controlled operations. One widely used approach involves superconducting circuits, where electrical current flows through loops of material cooled to extremely low temperatures. In these systems, the collective motion of paired electrons produces quantized energy states that can be assigned logical meaning. The circuit behaves as a macroscopic quantum object in which electrical properties are governed by wave-like behavior rather than classical particle motion alone. The distinction between different qubit states arises from measurable differences in energy configurations within the circuit. Another implementation uses trapped particles such as ions confined by electromagnetic fields in vacuum chambers. In this configuration, individual charged atoms are suspended in space and manipulated using precisely tuned laser light or microwave signals. The internal energy states of these ions serve as the basis for qubit representation. Because the ions are isolated from direct contact with surrounding matter, their quantum states can remain stable for extended periods under controlled conditions. The preparation of qubit systems requires extreme precision in fabrication and calibration. Superconducting circuits are constructed using lithographic techniques that define microscopic pathways for current flow, while trapped ion systems rely on ultra-high vacuum environments that eliminate nearly all background gas particles. Both approaches depend on the ability to reduce unwanted interactions that could disturb quantum states, making environmental isolation a central requirement of system design. Control of qubits is achieved through carefully shaped electromagnetic pulses that induce transitions between quantum states. These pulses are designed to match specific energy differences within the system, allowing targeted manipulation without affecting unrelated states. The timing, amplitude, and frequency of these signals must be precisely calibrated, as small deviations can lead to unintended evolution of the quantum system. This level of control allows sequences of operations to be performed that correspond to logical transformations in quantum computation. Measurement of qubit states involves interaction with classical devices that convert quantum information into observable signals. This process necessarily disturbs the quantum system, collapsing the superposition of states into a definite outcome. The design of measurement apparatus must balance sensitivity with minimal disruption prior to observation, ensuring that the quantum state is preserved until the moment of readout. The conversion from quantum information to classical data marks a fundamental interface between two different physical descriptions of reality. In superconducting systems, qubits are often implemented using structures known as Josephson junctions, where two superconductors are separated by a thin insulating barrier. This configuration allows quantum tunneling of pairs of electrons, producing discrete energy levels that can be manipulated externally. The behavior of these junctions is governed by both electromagnetic theory and quantum mechanics, creating a hybrid regime in which classical fields influence quantum states. In trapped ion systems, qubits are represented by stable internal energy levels of the ions themselves. Laser pulses induce transitions between these levels, allowing precise control over quantum states. The motion of the ions within the trap can also be coupled to their internal states, enabling multi-qubit interactions that form the basis of quantum logic operations. These interactions depend on shared vibrational modes within the trapping field, creating correlations between otherwise separated particles. Environmental isolation remains one of the most significant challenges in qubit realization. Even small amounts of electromagnetic radiation, mechanical vibration, or thermal fluctuation can introduce decoherence, causing quantum states to lose their structured relationships. Shielding systems, vacuum chambers, and cryogenic cooling all work together to reduce these disturbances, extending the lifetime of coherent quantum behavior. Despite these measures, maintaining long-term stability remains a central difficulty in scaling quantum systems. Error rates in qubit operations arise from imperfections in control, signals, material defects, and residual environmental interactions. These errors accumulate over time and must be managed through careful system design. Physical qubits are therefore engineered with redundancy and calibration protocols that allow errors to be detected and corrected before they propagate through computation. The physical nature of these corrections distinguishes quantum systems from classical ones, as they must operate within the constraints of fragile quantum states. As qubit systems increase in complexity, interactions between multiple quantum elements become essential for computation. These interactions are mediated through shared fields or coupling structures that allow entanglement to form between distant qubits. The resulting system exhibits collective behavior that cannot be described by independent state evolution alone. Instead, the entire network of qubits evolves as a single interconnected quantum system. Physical qubit realization therefore represents a convergence of material science, low-temperature physics, and quantum control engineering. Each implementation is constrained by the need to preserve coherence, while enabling precise manipulation and measurement. This balance defines the operational boundary between classical control systems and quantum mechanical behavior, forming the foundation for all subsequent layers of quantum information processing. Quantum state manipulation takes place within engineered environments, where external classical influences are carefully reduced, allowing controlled interactions to shape the evolution of microscopic physical systems. In this regime, quantum systems are treated as entities whose states are described by mathematical structures that correspond directly to measurable physical configurations. These configurations evolve in time according to well-established physical laws, but their outcomes are not deterministic in the classical sense. Instead, they are governed by probabilistic amplitudes that determine the likelihood of different measurable results. The manipulation of quantum states relies on external control fields, typically electromagnetic in nature, that interact with the physical system in precise and highly calibrated ways. These fields are generated by classical electronic equipment and delivered to quantum devices through carefully designed transmission pathways. The purpose of these signals is to induce controlled transitions between energy levels or other quantum states without introducing excessive disturbance that would destroy coherence. The balance between control and isolation defines the core challenge of quantum manipulation. In superconducting quantum systems, manipulation is achieved through microwave pulses that interact with Josephson junction circuits. These pulses are tuned to match specific energy differences between quantum states, allowing transitions to be driven with high accuracy. The phase frequency and duration of these signals determine the final configuration of the quantum system after interaction. Small deviations in control parameters can produce significant changes in the resulting state, highlighting the sensitivity of quantum dynamics to external influence. In trapped particle systems, manipulation is performed using laser fields that interact with the internal structure of individual atoms or ions. These laser interactions can excite transitions between energy levels, effectively rotating the state of the system within its quantum state space. The precision of these interactions depends on the stability of the laser frequency and the isolation of the particles from environmental noise. Coupling between internal states and vibrational motion within the trap allows more complex multi-particle operations to be constructed. Quantum state evolution under controlled manipulation follows continuous transformations that preserve the total probability of all possible outcomes. These transformations are reversible in principle, meaning that the system can return to its initial state if all interactions are perfectly inverted. This reversibility is a fundamental feature of isolated quantum systems and distinguishes them from classical dissipative processes where energy loss is unavoidable. The concept of interference plays a central role in quantum manipulation. When a system evolves through multiple possible pathways, the resulting probability amplitudes can combine in ways that reinforce or cancel each other. This interference pattern determines the likelihood of different outcomes after measurement. Control operations are designed to shape these interference patterns, guiding the system toward desired computational results. Entanglement can also be generated through controlled manipulation, linking the states of multiple quantum systems into a single correlated structure. Once entangled, the state of each system cannot be described independently of the others. Manipulation of one part of the system influences the overall structure of the combined state. This property enables complex quantum operations that rely on collective behavior rather than isolated components. The physical implementation of control sequences requires extremely precise timing. Quantum systems evolve continuously, and even small timing errors can lead to significant deviations in the final state. Control hardware must therefore operate with high temporal resolution, often synchronized to extremely stable reference oscillators. The coordination of multiple control channels is necessary to perform operations on multi-qubit systems without introducing unwanted disturbances. Noise remains a persistent factor in quantum state manipulation. External electromagnetic fields, material imperfections, and thermal fluctuations can all introduce unintended changes to the system. These effects must be minimized through shielding, filtering, and system design, but they cannot be completely eliminated. As a result, quantum manipulation always operates within a regime of controlled imperfection, where outcomes are shaped by both intentional signals and unavoidable environmental interactions. Mathematically, quantum manipulation corresponds to transformations within a high-dimensional state space, where each possible configuration of the system is represented as a point in an abstract structure. Physical operations move the system through this space along specific trajectories determined by applied control fields. The geometry of this space encodes the relationships between different states, including interference and entanglement structure. As quantum systems become more complex, the difficulty of precise manipulation increases significantly. Each additional quantum element expands the size of the state space exponentially, making full control of the system increasingly challenging. Despite this complexity, carefully designed control protocols allow useful operations to be performed on systems with many interacting quantum components. These operations form the basis of emerging quantum computational processes where information is encoded, transformed, and retrieved through controlled evolution of physical states. Quantum state manipulation therefore represents a finely balanced interaction between engineered classical control systems and inherently probabilistic quantum behavior. It operates at the boundary where deterministic external influence meets fundamentally uncertain internal evolution, creating a regime in which physical reality is guided but not fully determined by human-designed signals. Superposition of states appears within isolated quantum systems as a fundamental expression of how physical reality behaves at microscopic scales when it is not forced into a single definite outcome by measurement or strong environmental interaction. In this regime, a quantum system is described not as being in one specific state, but as existing in a structured combination of multiple possible states at the same time. Each of these possibilities contributes to the overall physical description of the system, weighted by quantities known as probability amplitudes, which determine how likely each outcome becomes when the system is eventually observed. At the physical level, superposition is not an abstract idea, but a measurable property of engineered quantum systems. In superconducting circuits, for example, electrical currents circulate in configurations that correspond to different energy states, and under carefully controlled conditions, the system can occupy a combined state that includes contributions from more than one current direction or energy level simultaneously. These combined configurations are stable only when the system remains isolated from external disturbances, since interaction with the environment rapidly destroys the delicate balance required to sustain them. In trapped particle systems such as ions held in electromagnetic fields, superposition manifests in the internal energy states of individual atoms. A single ion can be prepared in a condition where it is simultaneously described by multiple energy levels. Laser-based control techniques allow these states to be created, maintained, and modified with high precision. The resulting quantum state evolves continuously in time, with each component of the superposition contributing to the overall behavior of the system. The mathematical representation of superposition reflects a structure in which quantum states are treated as vectors in a high-dimensional space. Each possible state corresponds to a direction in this space, and a superposed state is formed by combining these directions in specific proportions. The evolution of the system corresponds to continuous movement within this space, guided by physical laws that preserve total probability. Although this representation is mathematical, it corresponds directly to measurable physical behavior in experimental systems. Interference arises naturally from the existence of superposition. When different components of a quantum state evolve, their probability amplitudes can combine in ways that either reinforce or cancel each other. This leads to patterns in measurement outcomes that cannot be explained by classical probability theory. In physical systems, interference is observed in experiments where particles or quantum states are split into multiple paths, and later recombined, producing results that depend on the relative phase relationships between the components. The stability of superposition depends strongly on isolation from the environment. Any interaction with external systems, even at extremely low levels, can introduce information exchange that disrupts the coherence between components of the quantum state. This process, known as decoherence, gradually transforms a superposed state into a classical mixture of outcomes. The rate of decoherence depends on factors such as temperature, electromagnetic noise, and material imperfections in the surrounding environment. In engineered quantum devices, maintaining superposition requires careful control of both internal system dynamics and external environmental conditions. Cryogenic cooling reduces thermal disturbances, while vacuum isolation limits particle interactions. Electromagnetic shielding reduces interference from external fields. Together, these measures extend the time during which superposition can persist, allowing meaningful quantum operations to be performed before decoherence dominates. Superposition also plays a central role in how quantum information is represented and processed. Unlike classical bits which exist in one of two definite states, quantum bits can exist in combinations of both states simultaneously. This property allows quantum systems to explore multiple computational possibilities at once, not as parallel classical computations, but as a single evolving quantum structure whose outcomes depend on interference patterns between state components. The evolution of superposed systems is continuous and reversible under ideal isolated conditions. This means that in principle, the system can be returned to its original configuration if all interactions are precisely controlled and reversed. However, in practical physical environments, perfect isolation is never fully achievable, and small interactions with the environment gradually introduce irreversibility into the system's behavior. Measurement transforms superposition into a single observed outcome. When a quantum system interacts with a measuring device, the combined system evolves into a state where only one outcome becomes accessible to observation. The process is governed by the physical interaction between the quantum system and the much larger classical apparatus, resulting in the apparent selection of a definite state from a range of possibilities. Superposition therefore represents a regime of physical reality in which multiple potential configurations coexist within a single structured system. It reflects the underlying quantum nature of matter at small scales, where deterministic classical descriptions give way to probabilistic evolution governed by interference, coherence, and environmental sensitivity. This regime forms a central layer in the progression from controlled quantum systems toward more complex interactions that involve entanglement and multi-system correlations. Quantum entanglement links arise when two or more quantum systems become connected through interactions that produce a single shared physical description, even when the systems are later separated in space. In this regime, the properties of each individual system cannot be fully described without reference to the others, because the overall state is defined collectively. This collective structure emerges naturally from quantum interactions, and does not require continuous physical contact once established. Entanglement typically forms when quantum systems interact in controlled environments, such as superconducting circuits or trapped particle arrays. During interaction, the systems exchange energy and information in a way that produces correlated quantum states. After this process, the combined system is described by a unified mathematical object that encodes all possible measurement outcomes jointly rather than independently. Each subsystem becomes a part of a larger interconnected structure that evolves as a whole. In superconducting platforms, entanglement is created by coupling qubits through shared electrical or magnetic fields. These coupling mechanisms allow the quantum states of separate circuits to influence each other, producing correlations in their measured properties. Once the interaction is established and then isolated, the entangled state persists as long as decoherence is minimized. The physical separation of the circuits does not remove the underlying quantum correlation that was established during interaction. In trapped ion systems, entanglement is generated through shared vibrational motion of ions, confined within electromagnetic traps. When ions are manipulated using laser pulses, their internal states become linked through the collective motion of the entire trapped system. This shared motion acts as a communication channel between particles, allowing operations on one ion to affect the joint quantum state of the group. The resulting entanglement reflects a deep connection between internal energy states and collective mechanical behavior. The mathematical structure of entanglement cannot be reduced to independent descriptions of each subsystem. Instead, the full state exists in a combined space that grows exponentially with the number of systems involved. This structure encodes correlations that are stronger than any classical statistical relationship. Measurements performed on entangled systems reveal outcomes that are individually random, but jointly correlated in a precise and predictable way. These correlations persist regardless of the spatial distance between entangled systems, provided that no external interaction disrupts the shared quantum state. This feature reflects the non-local structure of quantum descriptions, where the state of the system is defined as a whole, rather than as separate parts located in space. However, no information is transmitted faster than light through entanglement alone, since measurement outcomes remain fundamentally random at the individual level. Environmental interaction plays a critical role in the stability of entanglement. Decoherence processes gradually reduce the strength of quantum correlations by introducing uncontrolled interactions with surrounding matter and radiation. As entangled systems become more exposed to their environment, the delicate structure of their shared state breaks down and classical behavior emerges. Maintaining entanglement therefore requires isolation techniques similar to those used for preserving superposition, including cryogenic cooling and electromagnetic shielding. Entanglement is also sensitive to imperfections in control operations. Small errors in timing, pulse shape, or coupling strength can reduce the fidelity of entangled states, leading to deviations from ideal behavior. Experimental systems therefore rely on calibration procedures that continuously adjust control parameters to preserve the intended quantum correlations. These adjustments are essential for maintaining the integrity of multi-qubit operations in practical quantum devices. In computational contexts, entanglement serves as a resource that enables complex correlations between quantum bits. These correlations allow quantum systems to represent and process information in ways that cannot be replicated by classical systems. The presence of entanglement fundamentally changes how information is distributed across a system, creating structures that depend on the collective state rather than individual components. From a physical perspective, entanglement reflects the underlying interconnectedness of quantum systems that have interacted in the past. Once established, this connection is encoded in the structure of the quantum state itself, persisting until external disturbances destroy it. This persistence highlights the role of history in quantum systems, where past interactions shape present correlations. As systems become larger and more complex, entanglement can extend across many particles, forming highly structured networks of correlation. These networks are difficult to maintain because each additional system introduces new channels for decoherence. Nevertheless, controlled entanglement remains central to quantum computation and quantum information science, forming the basis for operations that depend on collective quantum behavior. Entanglement, therefore, represents a transition from isolated quantum behavior to deeply interconnected systems in which the properties of individual parts are inseparable from the whole. It establishes a new level of physical organization where relationships between systems become as important as the systems themselves, shaping the structure of quantum reality at its most interconnected scale. Decoherence from the environment represents the gradual loss of quantum coherence when a carefully isolated system begins to interact with its surrounding physical surroundings. At this level of description, a quantum system is no longer fully detached from external influence, and the delicate relationships between its internal states begin to degrade. The environment consists of all surrounding degrees of freedom, including stray electromagnetic fields, thermal vibrations, residual gas particles, and microscopic fluctuations within nearby materials. Each interaction, even if extremely small, contributes to the redistribution of quantum information into uncontrolled external channels. In an ideal isolated system, quantum states evolve in a reversible and coherent manner, preserving the structured relationships between probability amplitudes. However, perfect isolation is never fully achievable in practical physical systems. Even in cryogenic and vacuum environments, residual interactions remain. These interactions cause the quantum system to become entangled with the environment itself, extending the combined state into a vastly larger system that is not fully accessible to measurement or control. As a result, the original system appears to lose its coherent structure when observed independently. The process of decoherence does not require energy loss in the traditional sense. Instead, it involves the spreading of phase relationships between components of the quantum state into environmental degrees of freedom. These phase relationships, which are essential for interference effects, become effectively inaccessible when traced over the environment. The system then behaves as if it has transitioned from a pure quantum state into a classical statistical mixture, even though the total combined system remains governed by quantum laws. In superconducting quantum devices, decoherence is influenced by interactions with electromagnetic noise and material defects within circuit structures. Small fluctuations in magnetic fields or charge distributions can alter the phase of quantum states, gradually reducing coherence over time. The engineering of these systems therefore involves extensive shielding and filtering to suppress external noise sources and stabilize internal conditions. Despite these efforts, residual decoherence remains a limiting factor in the performance of quantum operations. In trapped particle systems, decoherence arises primarily from interactions with background radiation and imperfections in trapping fields. Even minimal collisions with residual gas molecules or fluctuations in electromagnetic confinement can disturb the quantum state of individual particles. laser stability also plays a role as small variations in frequency or intensity introduce unwanted perturbations into controlled quantum evolution. These effects accumulate over time, reducing the duration over which coherent quantum behavior can be maintained. The mathematical description of decoherence involves the reduction of observable interference terms within the system state representation. As the system becomes increasingly correlated with its environment, the distinct contributions of different quantum pathways become effectively separated. This separation prevents the observation of interference patterns that would otherwise arise from coherent superposition. The resulting behavior aligns with classical probability theory, even though the underlying system remains quantum in nature. Decoherence is a continuous process rather than an abrupt transition. The rate at which it occurs depends on the strength and frequency of environmental interactions, as well as the internal structure of the quantum system itself. Systems with stronger isolation or lower environmental coupling exhibit longer coherence times, allowing more complex quantum operations to be performed before classical behavior dominates. Conversely, systems with higher sensitivity to external disturbances experience rapid decoherence. Temperature plays a central role in decoherence dynamics. At higher temperatures, increased thermal motion leads to more frequent interactions between the system and its environment. This accelerates the loss of coherence. At extremely low temperatures, thermal contributions are reduced, allowing quantum states to persist longer. However, even at near absolute zero, other sources of noise remain, meaning that decoherence cannot be entirely eliminated. The concept of decoherence provides a bridge between quantum and classical descriptions of reality. It explains how classical behavior emerges from quantum laws without requiring a fundamental change in physical principles. Instead, classicality arises from the effective loss of accessible quantum correlations due to environmental interaction. This perspective allows classical physics to be understood as an emergent limit of quantum behavior under conditions of strong environmental coupling. In large-scale systems, decoherence occurs extremely rapidly, which is why macroscopic objects do not exhibit visible quantum behavior in everyday experience. The enormous number of environmental interactions at macroscopic scales ensures that coherence is destroyed almost instantaneously. This explains why quantum effects are typically restricted to microscopic or highly controlled laboratory conditions. Decoherence therefore defines the boundary between observable quantum phenomena and classical reality. It determines the practical limits of quantum information processing and shapes the design of all quantum technologies. By controlling environmental interactions, engineers attempt to extend coherence times and preserve quantum behavior long enough for meaningful computation and measurement. At its core, decoherence reflects the fundamental openness of physical systems to their surroundings. It demonstrates that no system exists in complete isolation, and that the structure of quantum reality is deeply dependent on interactions with the environment. This interconnectedness ultimately governs the transition from quantum possibilities to classical outcomes observed in the macroscopic world. Measurement and state collapse occur when a quantum system interacts with a macroscopic apparatus in a way that produces a definite observable outcome from a range of previously coexisting possibilities. At this stage, the system is no longer treated as an isolated quantum entity, but as part of a larger combined structure that includes both the microscopic system and the measuring device. The interaction between these two components creates a physical process in which quantum information becomes encoded into stable classical records. A measurement device is itself composed of many interacting particles that obey classical statistical behavior due to constant environmental coupling. When it comes into contact with a quantum system, The combined evolution leads to a rapid redistribution of quantum correlations across the larger apparatus. This redistribution causes the original coherent structure of the quantum system to become effectively inaccessible in isolation. The outcome appears as a single definite result, even though the underlying physical evolution remains continuous and governed by quantum laws. The concept of collapse refers to the effective transition from a superposition of possible outcomes to one observed result. In physical terms, this does not imply an instantaneous discontinuity in the fundamental equations of motion. Instead, it reflects the practical inability to track and reverse the full entangled evolution between system apparatus and environment. The observable effect is that only one outcome is recorded in classical memory, while alternative possibilities are no longer accessible. In experimental quantum systems, measurement is implemented through controlled interactions that amplify microscopic signals into macroscopic indicators. In superconducting systems, this may involve coupling a qubit to a resonant circuit that produces measurable changes in electrical response. In trapped particle systems, measurement may involve detecting emitted photons or changes in fluorescence when particles transition between energy levels. These amplification processes translate fragile quantum information into stable classical data that can be recorded and analyzed. The amplification step is essential because quantum effects at microscopic scales are not directly observable at human scales. Without amplification, the differences between quantum states would remain too small to detect reliably. The measurement apparatus therefore acts as a bridge between quantum behavior and classical observation, converting subtle quantum differences into robust physical signals that persist in time and space. During measurement, the quantum system becomes entangled with the measuring device. This entanglement spreads the quantum state across many degrees of freedom, including components that are not practically accessible. As the number of interacting particles increases, the system rapidly undergoes decoherence, which suppresses interference between different outcome branches. This process gives the appearance of a single outcome emerging from multiple possibilities. The selection of a specific outcome is not determined by classical causality, but by probabilistic rules inherent in quantum mechanics. Each possible result has an associated probability determined by the structure of the quantum state prior to measurement. The observed outcome corresponds to one realization of these probabilities, while the unobserved alternatives become part of the environmental record in a way that cannot be recovered. In macroscopic measurement devices, the amplification of quantum effects leads to irreversible information spreading. Once information about a quantum state is distributed across a large number of particles, reconstructing the original coherent state becomes practically impossible. This irreversibility is not fundamental in principle, but emerges from the extreme complexity of tracking all correlations within the combined system. Different interpretations of measurement exist within physics, but all agree on the empirical result that only one outcome is observed per measurement event. The physical description focuses on how interactions produce stable classical records, rather than on assigning independent reality to unobserved possibilities. The emphasis remains on measurable outcomes and their statistical consistency across repeated experiments. In quantum information systems, measurement plays a dual role as both a source of information extraction and a mechanism of state disturbance. The act of observation inherently alters the system being observed, preventing simultaneous access to all aspects of its prior quantum state. This limitation is a fundamental feature of quantum behavior rather than a technical constraint. The relationship between quantum systems and measuring devices illustrates the boundary between microscopic quantum dynamics and macroscopic classical reality. As systems scale upward in size and complexity, environmental interactions dominate enforcing classical behavior through continuous decoherence. Measurement represents the point at which this transition becomes experimentally manifest in a single recorded outcome. Measurement and state collapse therefore describe an emergent phenomenon arising from the interaction of quantum systems with large, complex environments. The appearance of definiteness reflects the spreading of quantum correlations into inaccessible degrees of freedom rather than a fundamental change in the underlying physical laws governing the system. Quantum error correction arises within quantum information systems as a structured response to the inherent fragility of quantum states under environmental disturbance and imperfect control. In this regime, information is not stored in a single physical element, but is distributed across multiple correlated quantum systems in a way that allows the original information to be reconstructed even when parts of the system are affected by noise. This approach is necessary because quantum states cannot be copied directly, and direct measurement destroys the information they contain. At the physical level, error correction relies on encoding a logical quantum state into a larger set of physical qubits. These qubits are arranged so that the information is embedded in correlations rather than in individual states. The redundancy is not classical duplication, but a carefully designed structure in which collective properties remain stable even when individual components experience disturbances. This distributed encoding allows certain types of errors to be detected without directly observing the quantum information itself. Quantum systems are continuously influenced by decoherence, which introduces random changes in state due to interaction with the environment. These changes can take the form of bit flips, phase shifts, or combinations of both, depending on the nature of the disturbance. Error correction protocols are designed to identify the presence of such changes indirectly by measuring auxiliary systems that reveal information about the structure of the encoded state without collapsing the underlying quantum information. In superconducting quantum devices, error correction is implemented using networks of coupled qubits that include both data qubits and additional measurement qubits. The data qubits store the logical quantum information, while the auxiliary qubits are used to detect deviations in the system. Controlled interactions between these qubits generate signals that indicate whether specific types of errors have occurred, allowing corrective operations to be applied without directly measuring the encoded information itself. In trapped particle systems, similar principles are applied using shared motional modes and internal energy states of ions. The collective behavior of multiple ions allows quantum information to be distributed across the system with certain configurations designed to be insensitive to localized disturbances. Laser-driven operations are used to entangle and disentangle qubits in sequences that reveal error syndromes while preserving the underlying logical state. The mathematical structure of quantum error correction involves encoding information into subspaces of a larger quantum state space. These subspaces are chosen so that certain types of environmental interactions move the system within the subspace without destroying the encoded information. When errors push the system outside the allowed region, correction protocols detect this deviation and apply operations that restore the system to its intended configuration. One of the central challenges in quantum error correction is the requirement for extremely precise control. Every additional qubit introduced for redundancy increases the complexity of the system and introduces new potential sources of error. The balance between adding redundancy and maintaining overall system stability is a fundamental constraint in the design of scalable quantum computing architectures. Error correction also depends on rapid and accurate measurement of error indicators. These measurements must extract information about the presence of errors without directly revealing the quantum state itself. This indirect observation allows the system to maintain coherence while still gaining enough information to correct disturbances. The speed of this process is critical, as delays can allow errors to accumulate beyond recoverable limits. In physical implementations, error correction cycles are repeated continuously. The system is constantly monitored for signs of deviation from its intended state, and corrective operations are applied in real time. This creates a dynamic balance between natural decoherence processes and engineered stabilizing mechanisms that work together to preserve quantum information over extended periods. Despite these techniques, error correction is not perfect. Residual noise, imperfect control, and finite measurement precision all contribute to limitations in performance. However, as systems improve, the threshold at which error correction becomes effective allows increasingly complex quantum operations to be performed reliably. This threshold represents a key milestone in the development of practical quantum computation. Quantum error correction therefore functions as a protective layer that enables fragile quantum information to survive in a noisy physical environment. It transforms vulnerability into structured resilience by distributing information across many interacting components. This transformation is essential for any large-scale quantum system, as it provides the mechanism through which coherent quantum behavior can persist long enough to support meaningful computation. At a deeper level, error correction highlights the fundamentally collective nature of quantum information. Information is not tied to individual particles, but to relationships between them, and stability emerges from the structure of these relationships rather than from isolation. This principle becomes increasingly important as systems scale toward larger and more complex quantum architectures. Scaling quantum systems introduces a shift in physical behavior as the number of controllable quantum elements increases from a small, well-isolated set to a complex interconnected network. In this regime, each additional quantum unit expands the dimensionality of the overall state space exponentially, meaning that the complete description of the system grows far faster than the number of physical components. This expansion creates a situation where direct tracking of every quantum interaction becomes physically and computationally impractical, even when the underlying system remains precisely governed by quantum laws. At small scales, individual quantum devices can be carefully isolated, controlled, and measured with high precision. However, as more qubits are added, interactions between them and their surrounding environment become increasingly difficult to suppress. Each qubit introduces additional pathways for noise, unwanted coupling, and decoherence. These interactions accumulate across the system, making the preservation of coherent quantum states progressively more challenging. The physical architecture of large quantum systems typically involves modular design, where groups of qubits are arranged into clusters that can be controlled and stabilized more effectively than a single large uniform array. These clusters are connected through controlled interaction channels that allow quantum information to be transferred or shared between different regions of the system. This structure reflects an attempt to balance scalability with the need to maintain coherence within manageable subunits. Control systems for large quantum architectures rely on highly synchronized classical electronics that coordinate timing signals, electromagnetic pulses, and measurement sequences across many components. As the number of qubits increases, the complexity of this control infrastructure grows significantly. Precise timing becomes increasingly important, since even small mismatches in control signals can lead to errors that propagate through entangled states and disrupt computation. Thermal management remains a central constraint in scaling quantum systems. Even though qubits operate at cryogenic temperatures, the supporting classical electronics generate heat that must be carefully managed to avoid disturbing the quantum environment. This requires layered engineering approaches where quantum components are separated from classical control hardware, while still maintaining efficient communication between them. Signal routing becomes increasingly complex as system size grows. Each qubit requires pathways for control and readout, and these pathways must be designed to minimize crosstalk and electromagnetic interference. As the density of connections increases, careful geometric and material design is required to preserve signal integrity. The physical layout of quantum processors therefore becomes a critical factor in overall system performance. Noise accumulation is one of the most significant challenges in scaling quantum systems. Even small imperfections in materials or control signals can accumulate across large networks, producing effects that are difficult to correct. Error correction techniques help mitigate this problem, but they also introduce additional overhead in the form of extra qubits and operations. This creates a trade-off between scalability and error tolerance that must be carefully managed. As systems scale, entanglement becomes more widespread and complex. Instead of involving only a few isolated qubits, entanglement can extend across large regions of the system, creating highly correlated structures. These extended correlations are essential for quantum computation, but they also increase sensitivity to environmental disturbance, since a disruption in one part of the system can propagate through entangled connections. The stability of large quantum systems depends on maintaining a balance between isolation and connectivity. Too much isolation prevents useful computation, while too much connectivity increases vulnerability to noise. Engineering solutions attempt to find optimal configurations where quantum information can flow efficiently without being excessively exposed to environmental disruption. Mathematically, the state space of a quantum system grows exponentially, with the number of qubits creating a structure that cannot be directly visualized or stored in classical memory for large systems. This exponential scaling is both the source of quantum computational power and the reason why simulation of quantum systems on classical computers becomes extremely difficult as size increases. Despite these challenges, incremental advances in hardware design, control precision and error correction continue to push the boundaries of scalable quantum systems. Each improvement extends the number of qubits that can be reliably operated, while preserving coherence long enough for meaningful computation. These developments represent gradual progress toward functional large-scale quantum machines. Scaling, therefore, represents a transition from carefully controlled laboratory-scale systems to complex engineered architectures where collective behavior dominates. The physical constraints of noise control precision and thermal stability define the limits of current technology, while also shaping the direction of future quantum system development. Quantum computational processes emerge when controlled quantum systems are guided through sequences of physical transformations that encode, evolve, and extract information from quantum states. In this regime, computation is not represented as a step-by-step manipulation of discrete classical symbols, but as a continuous evolution of a physical system whose state contains a structured combination of many possible outcomes. The computation is embedded in the dynamics of quantum states which evolve according to precise physical laws while remaining sensitive to controlled external influence. At the operational level, quantum algorithms are implemented through carefully designed sequences of control operations applied to qubits. These operations manipulate quantum states using electromagnetic pulses, coupling interactions and time-dependent fields that guide the system through a planned trajectory in its state space. Each operation modifies the probability amplitudes associated with different configurations, shaping how the system evolves toward a final, measurable outcome. A key feature of quantum computational processes is the use of interference to amplify correct solutions while reducing the likelihood of incorrect ones. As quantum states evolve, different computational pathways contribute to the overall state, with associated phase relationships. When these pathways recombine, their amplitudes can add or cancel depending on their relative phases. This physical interference process allows certain outcomes to become more probable than others, forming the basis of quantum computational advantage in specific problems. Entanglement plays a central role in enabling complex quantum computations. By linking multiple qubits into a single correlated system, entanglement allows information to be distributed across many physical components simultaneously. This distribution means that the system evolves as a unified whole rather than as independent parts, enabling computational structures that cannot be replicated by classical systems operating on separate bits. The resulting correlations are essential for capturing complex relationships within the computational problem. The evolution of a quantum computation is fundamentally reversible at the level of isolated physical laws. In principle, the system can be guided backward through its trajectory if all interactions are precisely controlled and inverted. However, in practice, interactions with the environment and measurement processes introduce irreversibility, meaning that only the forward direction of computation is physically accessible in realistic conditions. This distinction between theoretical reversibility and practical irreversibility is a defining feature of quantum information processing. Quantum circuits provide a structured framework for organizing computational processes. In this representation, sequences of quantum gates correspond to specific physical interactions applied to qubits. Each gate represents a controlled transformation that modifies the state of the system in a predictable way. The full computation is described by the composition of these transformations, which together define the final quantum state before measurement. Measurement is an essential part of quantum computation because it converts quantum information into classical outcomes. Without measurement, the results of a quantum process remain distributed across a superposed state and cannot be directly accessed. The measurement process collapses this distribution into a single observable result, which can then be interpreted as the output of the computation. The probabilistic nature of this outcome reflects the underlying structure of the quantum evolution that preceded it. Quantum computational advantage arises in certain classes of problems where classical systems require exponentially more resources to simulate equivalent quantum behavior. This advantage is not universal, but depends on the structure of the problem and the ability of quantum systems to exploit interference and entanglement. In these cases, quantum evolution explores many possible configurations simultaneously, with physical interference, guiding the system toward correct solutions. The physical implementation of quantum algorithms requires extreme precision in timing control and environmental isolation. Small deviations in control parameters can accumulate and alter the final outcome of a computation. As a result, quantum computational processes operate within tightly constrained physical conditions where noise decoherence and operational errors must be carefully managed. Error correction and fault-tolerant design are integrated into computational processes to maintain stability over long sequences of operations. These techniques ensure that quantum information remains coherent long enough for meaningful computation to occur despite the presence of unavoidable environmental disturbances. The integration of these stabilizing mechanisms is essential for scaling quantum computation beyond small experimental systems. Quantum computational processes therefore represent a physical realization of information processing based on the controlled evolution of quantum states. They operate through the interaction of coherence, entanglement, interference, and measurement, forming a dynamic system where computation is inseparable from the underlying physics. This framework defines a fundamentally different approach to information processing compared to classical digital systems grounded in the probabilistic structure of quantum mechanics. Computational complexity boundaries describe the limits that separate problems which can be efficiently solved using classical methods from those that become tractable only when quantum physical processes are used. In this regime, the focus shifts from individual machines to the abstract structure of problem difficulty as it is encoded in physical systems. The central idea is that the resources required to solve a problem are not only determined by algorithm design, but also by the underlying physical rules that govern information processing. In classical computation, the difficulty of a problem is often measured by how the required time or memory grows as the size of the input increases. Some problems scale in a manageable way, while others grow so rapidly in resource requirements that they become effectively unsolvable for large inputs. This scaling behavior reflects the limitations of sequential processing and the constraints imposed by classical physics on information representation and manipulation. Quantum computation introduces a different set of scaling behaviors because quantum systems evolve through the combined influence of superposition, entanglement, and interference. These properties allow quantum systems to represent and explore multiple configurations simultaneously within a single physical state. As a result, certain structured problems can be mapped onto quantum processes, where interference patterns guide the system toward correct solutions more efficiently than classical step-by-step evaluation. The comparison between classical and quantum computational boundaries is not based on individual examples, but on entire classes of problems. Some classes remain difficult regardless of quantum effects, while others show significant reductions in required computational resources when expressed in quantum form. This distinction reflects the deeper relationship between physical law and computational capability, where the structure of the universe influences what can be computed efficiently. In practical terms, quantum advantage appears in problems where the structure of the solution space allows interference to systematically enhance correct outcomes. This requires careful alignment between the mathematical structure of the problem and the physical dynamics of quantum systems. When such alignment exists, quantum evolution can suppress incorrect pathways while reinforcing correct ones through constructive interference patterns. However, not all computational problems benefit from quantum effects. Many problems remain equally difficult in both classical and quantum frameworks because their structure does not allow efficient encoding into quantum interference patterns. These problems continue to require exponential resources even when quantum systems are used, highlighting that quantum computation does not universally overcome classical complexity barriers. The boundaries of computational complexity are also shaped by noise and decoherence in physical systems. Even if a quantum algorithm offers theoretical advantage, real physical devices must maintain coherence long enough to complete the computation. Environmental disturbances can degrade performance, effectively limiting the size and duration of computations that can be reliably performed. This introduces practical constraints that sit alongside theoretical complexity limits. Error correction plays a crucial role in extending the reach of quantum computation into regimes where classical simulation becomes infeasible. By distributing information across many physical qubits and continuously correcting errors, quantum systems can maintain coherent evolution over longer computational sequences. This allows exploration of more complex computational spaces while preserving the structure necessary for meaningful results. From a physical perspective, computational complexity reflects the way information is embedded in and processed by physical systems. The exponential growth of quantum state space with system size explains why classical simulation becomes difficult, while also explaining the potential for quantum systems to access structured regions of that space more efficiently. The difference arises from how information is distributed and evolved under different physical rules. These boundaries are not fixed by human design but emerge from the fundamental laws governing matter and energy. They define what kinds of transformations of information are physically achievable within given resource constraints. Quantum systems do not break these boundaries but instead operate within a different region of the same physical framework, where alternative pathways through state space become accessible. As research continues, the mapping between computational problems and physical quantum systems becomes increasingly refined. Understanding which problems benefit from quantum behavior and which do not remains a central challenge in both physics and computer science. This ongoing exploration gradually clarifies the relationship between abstract computation and the physical structure of reality. Computational complexity boundaries therefore represent a deep connection between mathematics, information theory, and physical law. They define the limits of what can be processed, simulated, and predicted within both classical and quantum frameworks, revealing how the structure of reality itself constrains the nature of computation. Quantum information structure describes how information is physically encoded, distributed, and preserved within quantum systems where classical descriptions are no longer sufficient. In this regime, information is not stored as fixed localized values, but is embedded in the full quantum state of a system, which evolves continuously under physical laws. Each quantum state contains a complete description of all possible outcomes, represented through probability amplitudes that define how the system behaves when measured or interacted with its environment. At the microscopic level, quantum information is carried by physical degrees of freedom, such as electron spin, photon polarization, energy levels of atoms, or collective excitations in superconducting materials. These physical properties form the basis of quantum encoding, where logical information is mapped onto stable configurations of quantum states. Unlike classical bits which exist in definite states, quantum bits carry information through structured combinations of states that depend on coherence and phase relationships. The structure of quantum information is fundamentally relational. What matters is not only the state of an individual component, but also how that state relates to others within the system. Entanglement creates correlations that distribute information across multiple particles in such a way that the full description cannot be reduced to independent parts. This interconnected structure means that information is stored globally within the system, rather than locally in individual elements. Quantum information is also sensitive to phasor property that describes the relative alignment of wave-like components of a quantum state. Phase relationships determine how probability amplitudes combine through interference. Small changes in phase can dramatically alter the outcomes of measurements, making phase control a central aspect of quantum information processing. This sensitivity allows quantum systems to encode complex structures that depend on precise physical evolution. Decoherence plays a critical role in shaping the structure of quantum information by determining how long coherence and entanglement can persist. When a system interacts with its environment phase, relationships become dispersed across uncontrolled degrees of freedom, reducing the accessibility of quantum information. This process transforms structured quantum information into classical statistical mixtures, effectively limiting the duration over which quantum information remains usable. Quantum error correction techniques extend the stability of quantum information by embedding it into larger correlated structures that can withstand certain types of disturbance. In this approach, information is not tied to individual physical carriers, but to collective properties of many interacting systems. This redundancy allows the system to preserve logical information even when parts of the physical system are affected by noise or loss of coherence. The mathematical representation of quantum information uses vector spaces where each possible state of the system corresponds to a direction within a high-dimensional structure. Physical operations move the system through this space, altering the distribution of probability amplitudes. Although this representation is abstract, it directly corresponds to measurable physical behavior in experiments involving interference and entanglement. Measurement acts as the interface between quantum information and classical observation. When a measurement occurs, the distributed quantum information becomes localized into a single outcome. The rest of the quantum information becomes inaccessible due to entanglement with the measuring apparatus and environment. This process defines the boundary between quantum and classical descriptions of reality. Quantum information is inherently non-clonable, meaning it cannot be perfectly copied without disturbing the original state. This property arises from fundamental physical constraints and has important implications for information security and communication. It ensures that quantum information behaves differently from classical data, which can be duplicated without limitation. As quantum systems scale in complexity, the structure of quantum information becomes increasingly intricate. Large networks of entangled qubits form highly correlated systems, where information is distributed across many interacting components. These structures enable advanced computational and communicational capabilities, but also increase sensitivity to environmental disturbance. Quantum information structure therefore reflects a deep relationship between physical reality and the encoding of information. It demonstrates that information is not an abstract entity separate from matter, but is instead a property of physical systems governed by quantum laws. This perspective reveals information as an intrinsic part of the physical structure of reality itself. Fundamental physical interpretation brings the exploration to the deepest layer of quantum behavior, where quantum computation information and physical reality converge into a single unified description of how matter behaves at its most basic level. In this regime, the distinction between information and physical substance becomes increasingly subtle, as quantum states are understood not merely as mathematical abstractions, but as direct representations of physical configurations distributed across space-time and interaction histories. At this level, reality is described through quantum fields that permeate all of space, with particles emerging as localized excitations of these underlying fields. Each excitation carries properties such as energy, momentum, and charge, but these properties are not fixed classical attributes. Instead, they arise from quantum states that encode probabilities for different measurable outcomes. The structure of these states determines how physical systems evolve and interact, forming the foundation for all observable phenomena. Quantum computers operate within this same framework, manipulating physical states in controlled ways that reveal the computational potential of quantum evolution. The behavior of qubits reflects the underlying field dynamics, where superposition and entanglement are not external features but natural consequences of quantum field interactions. The computation itself is a physical process inseparable from the evolution of the system's quantum state under carefully engineered conditions. At this fundamental level, uncertainty is not a result of incomplete knowledge, but a built-in feature of how physical reality is structured. The probabilistic nature of quantum outcomes reflects limits imposed by the structure of quantum states themselves. Even with perfect information about a system's state, only statistical predictions about measurement outcomes are possible. This intrinsic uncertainty defines the boundary between deterministic classical intuition and quantum physical behavior. Entanglement reveals that spatial separation does not imply independence at the quantum level. Systems that have interacted in the past retain correlations encoded in their shared quantum state regardless of distance. These correlations do not transmit classical signals, but represent a deeper structural connectedness within the quantum description of reality. The universe at this level behaves as a single interconnected system evolving according to unified physical laws. Decoherence explains why classical reality emerges from this underlying quantum structure. As systems interact with their environment, quantum correlations spread into increasingly large and complex degrees of freedom. This process effectively hides quantum behavior at macroscopic scales, producing the stable classical world of everyday experience. Classical reality is therefore understood as an emergent approximation of a deeper quantum substrate. Quantum computation exists as a controlled expression of this deeper structure, where engineered systems temporarily suppress decoherence to harness quantum evolution for information processing. The same physical laws that govern natural systems are used deliberately to guide quantum states through computational pathways. This reveals computation not as an abstract logical activity, but as a direct manipulation of physical reality at its most fundamental level. The boundary between computation and physics becomes indistinct in this interpretation. Every computational step corresponds to a physical transformation of quantum states, and every physical evolution can in principle be interpreted as information processing. This equivalence suggests that information is not separate from physical law, but is embedded within it as a fundamental aspect of reality. At the deepest conceptual level, quantum systems do not represent hidden variables or deterministic structures beneath randomness. Instead, they define a probabilistic framework in which outcomes emerge from the structure of quantum states interacting with measurement processes. Reality is thus understood as a continuous unfolding of potentialities, constrained by physical law rather than predetermined trajectories. Quantum computers in this context do not reveal hidden secrets of a separate computational realm, but instead expose features already present in the structure of physical reality. Their operation highlights the ways in which quantum systems naturally explore multiple possibilities simultaneously shaped by interference and entanglement. This behavior reflects the intrinsic architecture of the universe at microscopic scales. The overall interpretation that emerges is one in which reality, information, and computation are deeply intertwined aspects of a single physical framework. Quantum systems reveal that what is observed, what is computed, and what physically exists are not separate categories but different perspectives on the same underlying processes governed by quantum laws. In this final layer, the exploration returns to a stable equilibrium of understanding. Quantum computers do not stand apart from reality, but are embedded within it using the same principles that govern all physical systems. The apparent strangeness of quantum behavior reflects not an anomaly, but the fundamental structure of the universe itself expressed through the language of probability correlation and evolving physical states.